Hi everyone. This lesson is going to be on 6.3, specifically Pascal's triangle and its application to help with binomial expansion. The video will be in two parts. The first one, I need to first introduce what the heck Pascal's triangle is. So I'm going to be explaining this, looking at all the different intricacies, all the different interesting parts to it and familiarize you with it before we actually apply it and learn what binomial expansion actually is. To efficiently learn Pascal's triangle, we do need to recap how to write out different notations for a term in a sequence. So recap again. In a sequence, a term notation is going to be written as Tn. That was a terrible Tn. In case you remember, Tn. Right? Where term, and that would be the number in the sequence, or the order, rather. What I mean by that would be, for example, if I say T1, that would be the first number, or the first term in the sequence, whatever that sequence might be. Okay. Hope that's not something surprising. Pascal's triangle is going to use a modified version of this, so be flexible. Don't take this and be like, oh, it's changed, it's a completely new thing, Mr. Kim, you're going crazy. That's not the goal here. Just for the sake of space, I'm going to erase all this. So remember how to write term. Again, my expectation is that you already know how to do this because you've been working really hard in practicing the homework that was assigned to you. Pascal's triangle is a special sequence of numbers written in multiple rows. Pascal's triangle, without any explanation, is a sequence of number that looks like this. I start with the 1, and that 1 is going to move to the left and right, creating the next row as 1 and 1. So this one drops down to the left, creating a 1, it drops down to the right, creating a 1. This pattern continues on. But what happens in the next row? It gets sort of interesting. If this one moves to the left, nothing special there. If the 1 on the right continues moving right, I have a 1. But if the 1 from the left side and the 1 from the right side move in according to these arrows, I have 1 twice. So what is 1 plus 1? The number in between, so the second number, so the middle number in the next row is a 2. If I were to continue, can you continue this pattern for me? This 1 will create a 1. 1 and a 2, the sum of 1 and 2 would be 3. The sum of 2 and 1 would be 3. And of course, that 1 just drops down. It's 1, 3, 3, 1. You can guess before I write on what the next one would be. Going once, going twice. 1, 4, 6, 4, 1. If you're still sort of confused of where this is coming from and why we're adding this, think about this as a natural occurrence in a variety of different things in life. One example might be comparing it to a champagne tower. You might have seen something, tower, I can't spell. You might have seen something like this in movies and stuff. Here's the first champagne glass or whatever. And that glass is balanced on top of 2 other glasses. Right? And these 2 glasses are balanced on top of 3 identical cups of the remaining of the top. And these 3, of course, are balanced by 1, 2, 3, 4 cups. Identical, of course. Please excuse my poor drawing. So let's get to it. If I start pouring my drink into the first glass until it begins to overflow, Let's just talk about that one. The rate in which we fill that glass, let's pretend it's just 1 because it's the simplest number. As it begins to spill over, without getting too technical here, and if this is a perfect world, does the speed in which the left glass fills, is it any different than the speed in which the right glass fills? I'm going to argue no. So the rate that the left glass fills and the right glass fills are equal. I'm just going to call them 1 and 1. Okay? But let's continue on because, again, it gets interesting after the second, I guess, set of cups. If this glass fills at a rate of 1 and the right glass fills at a rate of 1, the middle glass is getting champagne from both left and right glasses. In essence, the middle glass will fill twice as fast as the glass on its left and right. So we write 1, 2, and 1. And if I were to continue that, yes, you people who are super technical and want to challenge me will probably say that's not completely true and blah, 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 blah. You'll have some missing or spilling or whatever. But bear with me. The pattern in Pascal's triangle follows this type of example and simply just continues to add the two numbers right above it on its left side and right side. That would be a 4. That would be a 6. That would be a 4 and 1 and 1, so on and so forth. So this is Pascal's triangle. Now, why is it called Pascal's triangle? Well, Blaise Pascal is a French mathematician who is, I guess, attributed to its fame and fortune, I suppose. But he wasn't actually the first person who knew about it. Closer to 1300s AD, in a Chinese textbook, you would see a reference to the exact same pattern on it. So this was over 300 years before Blaise Pascal was made famous for this pattern. But why was Blaise Pascal given credit? Simply because Pascal was the first person who actually did something with it. That's all. Okay, so this is Pascal's triangle. What is so special? Pascal's triangle creates a variety, just a plethora of different patterns. This pattern of 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. There's so many different patterns, sequences, if you will, sort of embedded inside it that honestly, I can't cover it. I'll just bore you with trying to talk about all of them. But maybe I can at least convince you that it is a very special tower, a very special pattern, so that you will pay a little bit more attention and give it a shot in working with it. And please note, the reason why I'm trying to get you to be familiar is because our final goal is binomial expansion in the next video. That's our ultimate goal. So use this time to get familiar with it. I'm going to write out Pascal's triangle clearly so that I can show you as many patterns as possible. 4, 6, 4, 1. At this time, if you haven't done so already, and if you've just been listening to me, you might want to bust out a piece of paper and start your own Pascal's triangle. Bust out some highlighters because you are going to be in for a ride. All right, starting off, what is so special? Again, as I said before, there are a bunch of different patterns in here, but to make patterns easier to identify or to make sense of it, we're going to start by labeling these rows and these terms inside each row, starting with the number 0. Okay, so again, bear with me. This first row is row 0. Next one will be row 1. This is row 2, row 3, row 4, row 5, row 6, and honestly, it goes to infinity. Okay. Why do we write it this way? Number one, for convenience. Here's one reason why we do it, out of convenience. The diagonal that has all the ones, it doesn't do anything special for us. But take a look at the second diagonal. The second diagonal seems to correspond, let me do that nicer, seems to correspond with the actual row number. It just so happens that we start from 1 and we're counting up. Hence, this triangle is actually this diagonal is actually referred to as the counting numbers. Okay. And why do we use row 0 as my first row? Here's my first pattern. Please take a look at the sum of every single row. The sum of row 0 is 1. The sum of row 1 is 2. The sum of row 3 is 4. The sum of row 4 is 8. The sum of row 16 is 1 plus 5, 4, 5, 11, 15, 16. And by now, you might recognize some of these numbers. 1, 6, 16, 26, 31, 32. And 1, 7, 22, 42, 52, 57, 63, 64. Do these numbers look familiar? These are exponents with base 2. Keep going. What do you notice about the exponent number and the row number? Yeah, I don't mean to be, someone that says, a teacher that says, I told you so, and be all smart aleck and giddy about mathematics, but yeah, it's a coincidence, or maybe not. Okay, so this is one of the reasons why we start with row 0. It just sort of makes sense. Another reason, take a look at this one. Do you notice how there's a 1 here and a 1, 1, which sort of looks like 11? 1, 2, 1, which sort of looks like 121? 1, 3, 3, 1, which sort of looks like 1,331? Well, what is I need a different color. What is 11 to the power of 0? 1. What's 11 to the power of 1? 11. What is 11 to the power of 2? 121. What is 11 to the power of 3? 1,331. What's 11 to the power of 4? 1 4. I think you get there. What is 11 to the power of 5? What the heck is that? There's a little trick involved. Anytime it goes to the tens, it's actually added to the previous number. So the number actually does work for Pascal's triangle. It's 1, 6. Let's see, 1, 6, 1, 0, 5, 1. And it goes on. Once again, do you notice something interesting about the row number here? Coincidence? Maybe, maybe not. There's a couple of others I can do. Is there a couple of others I can do? How about I give you one more just so that you're convinced that this is a special triangle. Using a highlighter, take a look at this pattern. I am going to go about starting from any one of these ones and create a shape that looks sort of like a hockey stick. 1, 3, 6, and 10, and then create a little hockey stick by going to the next row and down to the right. When creating a hockey stick, you will find that all the numbers that are in the stick portion add up to the number in the, what do you call this, the paddle portion? I don't know. Think about it. 1 plus 3, that's 4. Plus 6, that's a 10. Plus 10, that's a 20. Bam. Okay? Just to prove a point, 20 plus 15 is 35 is the next number. Let's do it. How about I take a pick? 1 plus 4 plus 10 plus 20. Does it create 35? 1 plus 4 is 5, plus 10, 15, plus 20, 35. Every time I create a hockey stick, the final number is the sum of all the numbers that are involved in the stick portion, in the handle portion. Okay. This is Pascal's triangle. So hopefully I've convinced you that Pascal's triangle is a bit of a special sequence. But knowing that there are both numbers in each row and multiple rows, how do we refer to the term number? When we started this lesson, I talked about Tn. Well, Tn isn't going to be sufficient if you have multiple rows or multiple sequences. So we need something else. Okay, let's erase that. When we're talking about Pascal's triangle, we are going to need to talk about all of this as a term of a certain row and a certain number in the sequence. Okay, a certain order in the sequence. Once again, when we're talking about Pascal's triangle, you're going to see two numbers next to t instead of one. The first number refers to the row number. The second number refers to, I'm going to say, the term number in the row. And both of these start at 0. Okay? What do I mean by that? I'm going to take Pascal's triangle on the top left. I'm going to convert it into the top right. Sorry, bottom right. Let's see if you can do that with me. Can you do that as an exercise? The first value is in the 0th row, and it is the 0th term. So t0, 0 is referred to as 1. What about the next one? These two 1 values are in the first row. The first one is actually the 0th term. So take a look. In the first row, the 0th term is 1, and in the first row, the first term is 1. I know it's a little weird, but Pascal's triangle requires a different system, so okay, try to get used to it. The next, in the second row, the 0th term is a 1. In the second row, the first term is a 2. And the second row, the second term is a 1. Notice how the term number in the row never gets larger than the row number. Next, in the third row, the 0th term is a 1. In the third row, the first term is a 3. In the third row, the second term is a 3. And in the third row, the third term is a 1. Getting the hang of it? Try the next line without me saying anything. We can pause the video. The answer that you should have gotten would be, again, if you haven't done so, pause the video and do it now. Hope you got it. Okay. For any given term, you can refer to it using the term notation, row number, term number in the row. All right. So continuing on with this term notation, how do we write any kind of explicit formula for Pascal's triangle? Well, in essence, you can't really. Every number in Pascal's triangle is requires the terms in the previous row. Ring a bell? For Pascal's triangle, the only way we can write formulas is writing the explicit formula. For as an example, let's take this one, T42. To get the value of 6, I need the value from term 3.1 and term 3.2. Another way I could write it is, I need the value from the previous row of 4, the same term number as the 2, and 1 just before it. Okay, the recursive formula for Pascal's triangle is T n comma r equals the previous row's previous term plus the previous row's same number term. Pascal's triangle. Hope you're getting by. Please, your job for this video is to become very, very comfortable with this term notation of Pascal's triangle. Be very, very comfortable using the recursive formula to work different questions out. And also, of course, to be able to write out the Pascal's triangle for as long as you need to. Why is that? Well, in future, you might get questions that require you to identify a certain value. Like, for example, if I asked you, hey, what is the term number, what is the value of the third term of the 11th row in Pascal's triangle? Well, using the recursive formula idea, the only way you can do that is if you know the 10th row. If you need the 10th row, you need to know the 9th row. If you know the 9th row, you need the 8th row. You need the 7th row, 6th, 5th, 5, 4, 3, 2, 1. You need to be able to write out Pascal's triangle very quickly. So get to practicing. Okay? Now, as you might imagine, if you know me, anything that's rigorous and really annoying, there's always a shortcut. There's always a way to get around it because mathematicians are lazy. So if you want to know another way to quickly calculate it, it requires you to use a button in your calculator without knowing why just yet. So if you're like, no, that's not for me, I know how to do this, I can do Pascal's triangle really quickly so that I can answer whatever question I want, go ahead. Okay, just go ahead. You could stop the video now and just memorize it. If you are willing to try and memorize the shortcut using the calculator for now, or if you are planning on taking data management next year, continue watching. If not, or you're just not ready for it, or you don't care for it, stop the video and go practice page 378, numbers 2 to 4. Go do that now. For everyone else who is willing to try out this shortcut, I am going to ask you to quickly fast forward to the timestamp below so that you don't have to waste any time watching me erase all this, and bust out a calculator. You will need it. The button you are going to use in your calculator is this button called, sorry, it's black. The button you are going to use in your calculator to quickly get any value in Pascal's triangle looks something like this. N, big C, R. Little n, big C, R. This is, it's a kind of, you know what, it's called, let's just say that when you get into probabilities and permutation and computation and whatever, this is going to be one of your best friends. Okay, for now, if this is called computation. Okay, and just as we were talking about NR, the number on the left is going to be your row number, and R is going to be the term number you are interested in. Okay, and it's commonly written in data management textbooks like so. N and R written on top of each other with a large bracket surrounding both of them. Okay, so what is the shortcut? Let's pretend, just like before, you wanted to know what T11, 3 is going to be. Okay, That means the row is 11 and the term number is 3, which means it's the fourth number in the sequence. Take your calculator. What you're going to type in is 1, 1 for 11. You're going to type in Shift and press whatever button that lets you do MCR. And you're going to type in 3 and the equal sign. If you do that, you will see that it is going to give you 165. And if you continue this all the way to 11th row, you will find that the fourth term is 165. That might be a little bit far. How about we try a different question, a number that we already know. Pop quiz. What is the term notation for the number 20 in the 6th row? Pause now and think about it. Going once, going twice. Have you thought about it? Number 20 would be n of 6, r of 3, right? 20 is in the 6th row, term 0, term 1, term 2, term 3. So on your calculator, figure out what 6CR or 6 choose 3 is. The calculator should be able to spit out 20. Okay, again, just for the sake of familiarity, you can also write it as 6, 3 on top of each other. Again, you don't need to know exactly why this is the case. You will learn it in data management, but for now, know how to use a calculator. It does save a lot of time. Okay? And so, please, just because you have this shortcut doesn't mean you don't need to know the recursive formula for Pascal's triangle. The main goal is to familiarize yourself with Pascal's triangle and especially be able to spit out any term of any row. If you can do that, you are ready for the next jump, which is using Pascal's triangle for binomial expansion. Okay. Close the video now and try practicing page 378, numbers 2 to 4 before watching the next one. Good luck. Send me emails for questions if you need, and I hope to see you soon. Bye.